In this tutorial, we're going to take a look at solutions to a test. This is a test review for the Advanced Functions course, and the topic is rational functions. And so we're going to go over all the answers to this test review in a fair bit of detail, even the multiple choice at the beginning in the first page here. So the first question asks, what is the domain of this g of x function? And rational functions often have some restrictions on the domain. It's usually all real numbers with the exception of a few numbers. And you get those restrictions by setting the denominator is equal to 0. Now, if the denominator was not factored here, we'd factor it. You could use the quadratic formula. If it happened to be bigger than a quadratic, you could use long or synthetic division to factor it. But you're looking for the individual factors of the denominator so you can set them all to 0. And so I set x plus 1 equal to 0 and subtract 1 from both sides, so I get x equals negative 1. So negative 1 is a value that would make that denominator factor 0, so hence the function would be undefined. Because if the denominator has a value of 0, 0 times anything else would be 0. If you're dividing by 0, then you can't do that. It's not defined. We also set the 5x minus 2 equal to 0, so add 2 to both sides, 5x equals 2, and then of course I want to solve for x here, so I would divide both sides by 5, like that. And of course the purpose of that, so those 5s divide out, and I get x equals 2/5. So 2/5 is the value that would make that factor 0. So the restrictions are x can be, or actually the domain, is x is all real numbers such that x can't be negative 1 or 2/5. The factors in the numerator have nothing to do with any restrictions, because if that factor was 0 or this factor was 0, well, the function just equals 0. And that's okay. You just can't have a value of 0 in the denominator because you can't divide by 0. On to number 2. Rational functions are defined to be a blank divided by a blank. And the best solution here is answer is a polynomial function over another polynomial function. B is a kind of, B happens sometimes. Sometimes you might have a constant function over a polynomial. That can happen, but in general it's not always going to be a constant on top. In number 3 here, if I were to cover up the x and you have negative 7 over 6x plus 5, that would be a constant over a polynomial, but often it's some function of x in the numerator as well. So C is the best answer for question number 2. In number 3, what's the horizontal asymptote for this? You look at the ratio of the dominant term in top to the dominant term in the bottom, the largest power of x in each. See, the plus 5 becomes insignificant because if you think of, it's how the function behaves for large values of x. And when I say large values of x, I don't mean numbers like 8 or 17. I mean numbers in the hundreds, thousands, or millions, or even bigger. So the plus 5 becomes insignificant if x is large. Think of if x was 1,000,000, 6 times 1,000,000 would be 6 million. So let's say it was money. Let's say you had $6 million. If somebody came up to you and said, oh, I'm going to give you $5. Well, that's not very significant if you already have 6 million. So you might just say, keep the $5. Okay. So the 5 is insignificant if x is very large. So we drop it and just take the ratio of the dominant term on top and bottom. So that's why I wrote negative 7x over 6x here. And so the x's divide out. So we're going to cross the x's out like that. And so the horizontal asymptote is just y equals negative 7/6. So C is the correct answer for number 3. 2 C's in a row. Number 4, rational functions can have at most, and we're looking for a number here, horizontal asymptotes. And 1 is the correct answer, A. There's only one limiting value that the function can get close to, because that's what a horizontal asymptote is. If x is really big, what's this function being approximated by? So there's only one of them, there's not 2 or more. There can be more than one vertical asymptote. For example, in number 1 here, x equals negative 1 and x equals 2/5 would be 2 different vertical asymptotes. And if there was a third or fourth factor or fifth factor, there could be 2, 3, or 4 or 5 different vertical asymptotes. Flipping on to part 2. Part 2 is the questions where you have to start showing your work. And this page and the next one take a look at graphing a couple of rational functions and another one that's slightly different later on. So this first one is actually an example of a constant over linear function because it's 10 over x minus 5 we're graphing. And so you're asked to find the asymptotes and intercepts of any and show how to get the end behavior near those asymptotes. So first of all, I'm going to find the vertical asymptote. So I would set the x minus 5 factor in the denominator equal to 0 and solve for x. So if we add 5 to both sides of that, we get x equals 5. And so there's the vertical asymptote, x equals 5. We'll get into the behavior in a little bit. The horizontal asymptote is y equals 0. And it's y equals 0 because there's only a constant on top, but there's actually a function of x in the denominator. And I'm going to bring my graphing calculator over here and show you. So let's say x was 100. I'm going to put 100 in place of x. So we would evaluate that. Okay, you get 0.10526. Let's say that x is bigger now. Let's put another 0 in there. So x is 1,000, 0.01. And let's go even bigger. Go back and insert another 0. So x is 10,000, 0.001. So it's actually, notice it's getting quite close to 0. And so that's why y equals 0 is the horizontal asymptote. You see, basically, as x becomes big, it's 10 divided by a larger and larger number, and so that's why it's tending towards 0. Now, for the intercepts, there is no value of x that would make this 0. And to show you why, I'm going to multiply both sides. That's what these are for here. If I wanted to solve for x here, I would multiply both sides by x minus 5. So over here on the left, this x minus 5 would divide out with that one. And so we'd just be left with 10 equals. And on the right, when I multiply the 0 by this x minus 5, I get 0. So I get the ridiculous statement that 10 equals 0. So I get an inconsistency. If you've algebraically done nothing wrong, and you get an inconsistency like that, then that means there's no solution. So that's why there's no x-intercept. And it should make sense too, because if the horizontal asymptote is here, then that means the graph is not probably going to cross that. Okay? There are a few rare cases where you can cross a horizontal asymptote, but it really doesn't happen very often. The y-intercept can be found by putting 0 in place of x. So we put 0 here and here, we get 10 over 0 minus 5. 10 divided by negative 5 is negative 2, so 0, negative 2, which is that point right there, is the y-intercept. And the rest of this is actually end behavior around the vertical and horizontal asymptotes. So in all these examples, I'm going to do the horizontal first. And the horizontal or end behavior near the horizontal asymptote is what happens if x is large to the far right or the far left? How are you getting close to that asymptote? So I put a number like 100 or 1,000 in place of x. So it would be 10 over 100 minus 5. And actually, that's the same calculation I just did here. 0.105. Notice it's getting close to 0 again, but they're all positive, because if I'm putting a positive large number in place of x, then it's 10 divided by a large positive number. So it's going to get close to 0 but stay positive. So that means as x tends towards infinity, we're approaching 0, and this little plus here kind of looks like an exponent. It means we're approaching 0 from the positive side. So what it's doing is if we come down here, we're getting closer to the asymptote, but we're staying above it on the positive side. If we want to know what happens here, as you go to the far left, substitute a number like negative 100 in place of x. So it would be 10 over negative 105, which is negative 0.095, etc. So it's getting close to 0 still, but it's negative because we're dividing a positive by a negative. So as x tends towards negative infinity out to the far left, you approach 0 from below. That's what that minus there means. So as we come past the y-axis intercept there, we're getting closer to the asymptote, but we're staying below it. Now the only other thing to talk about is what the end behavior is around the vertical asymptote. Remember, that was x equals 5. So 4.99 is a little bit to the left of 5, so I put a number like that in, and then also a number a little bit above 5. Okay, left of 5, right of 5, but really close. So if I put 4.99 in place of x here, it works out to a function value of negative 1,000. And so, okay, that's to the left of 5. So as we approach 5 from the left, that's what that negative means. The y values are tending towards very large negative values. So we say y is tending toward negative infinity. So that means that as you pass this here, come towards the right and get closer to where x is 5, the y value is becoming larger and larger negatives. It's going like that. And so what happens up here is If you approach 5 from above, so 5.01 for example, to the right of 5 just a little bit, then the function value works out to positive 1,000 in this case. So as x approaches 5 from the right hand side, y tends towards infinity, like large positive values, and so that means the function does this. It goes up and up and up the closer you get to 5 from the right hand side. And that's number 1. Question number 2, sketch the graph of this function. So in this case, we have a linear over a linear function. No constant anymore on top except for the minus 10. So the vertical asymptote will set the denominator, the 4x plus 12 equal to 0. Subtract 12 from both sides, so 4x would equal negative 12. And divide the 4, and you get x equals negative 3. So there's the vertical asymptote right there, x equals negative 3. For the horizontal asymptote, the negative 10 and 12 become insignificant in what they contribute to the function if x is really big. Again, think of x as 100,000 or a million. 4 times 100,000 and then plus 12 isn't much different than 4 times 100,000. Okay, so we drop the negative 10 and 12. Remember, it's just dominant term in x in the numerator divided by dominant term in the denominator, which is 5x over 4x. And those x's divide out, so they divide out, so we just get 5 over 4, which of course 5 divided by 4 is 1.25. And that's going to be an important number to remember just a little later on in the question. So that's the horizontal asymptote at y equals 1.25 there, a little bit above y equals 1. Now intercepts. We can find the y-intercept by setting x to 0. So we put 0 in place of x here, here, and here. And of course this is all 0, so we just get negative 10 over 12, which would reduce to negative 5, 6. And so 0, negative 5, 6, which is that point right there, slightly above negative 1, is the y-intercept. There is an x-intercept in this case. So if you take the function and set it equal to 0, I want to solve for x here, then what I would do is multiply both sides by 4x plus 12, the denominator here. And of course the purpose of that is so that those divide out. And so I would just get the 5x minus 10 equals, now 0 times 4x plus 12 is 0. So this actually just collapses to 0 on the right. So we have 5x minus 10 equals 0. And I want to solve that for x, so I would add 10 to both sides. So I get 5x equals 10, and then divide out the 5. They're gone, and that equals 2. So that is the x-intercept. We're at 2, so 2 comma 0 is the x-intercept. Now, end behavior. Let's look at the horizontal first. Where is it below and above? So again, put a large positive and a large negative number in place of x, like 100 and a negative 1,000, negative 100, or 1,000 and negative 1,000. I did 100, so here's my hundreds here, and the function value at 100 is 1.1893 approximately. Now, so this is where the 1.25 comes in, is important. So that's getting close to 1.25, but it's a little bit below it. So as x tends towards infinity to the far right, a big positive number, y is approaching 1.25 but from below, because we're below the 1.25 here. So that means as you come out here, we're staying below the horizontal asymptote. If we go to the far left and put a number like negative 100 or 1,000, negative 100 gives us a function value of 1.3144 approximately. That's a little bit bigger than 1.25. So as x tends towards negative infinity to the far left, y is approaching 1.25 but from above, because this is bigger than 1.25. So that means as you go to the far left here, you're staying above that horizontal asymptote. So the vertical, okay, what happens around this x equals negative 3 line? So negative 2.99 is slightly to the right of negative 3. So if I put that in place of x, I get negative 623.75. Remember, that's to the right of the vertical asymptote. So as we approach negative 3 from the right side, the positive side, the y values are tending towards very large negatives. Y tends towards negative infinity. So as we come through our intercepts here, getting close to larger and larger negative y function values. So it's going down. This is slightly to the left of where x equals negative 3. And so f of negative 3.01 works out to 626, almost the opposite of this number. So large positive function value. So as we approach negative 3 from the left, the function values are y values approaching infinity, large positives. So that means as you come you get closer to that vertical asymptote from the left side of it, the function value is becoming very large positives and going up like that. And so that's number 2. Question number 3, and on this page there's 3 rational equalities to solve. So the first one, the x plus 9 over 2 equals 5x. Rational equalities, I want to multiply both sides by a number so that the denominators all divide out and I don't have any rational expressions anymore. The only denominator in the first case is 2, so that's why this x plus 9 is getting multiplied by 2 and the 5x is also getting multiplied by 2. That's a multiplication sign, that's an x. There's a little graphical difference between them. So the 2's divided over here and you're just left with x plus 9 on the left. 5x times 2 would be 10x. And I want to rearrange and get the x's on one side, numbers on the other. So I would subtract x from both sides. Okay. Some people use the terminology bring the x over. We are actually subtracting x to do that. So 10x minus 1x is 9x, just a 9 left on the left. Divide out that 9. Those 9's divide out. 9 divided by 9 is 1. So x equals 1 is the solution to this first one. Question B over here. There's actually denominators in all these, although these two are the same. So the only 2 different factors are x minus 1 and x plus 2. So the least common denominator would be the product of x minus 1 and x plus 2. And so that's why I will multiply this by x minus 1, x plus 2, this right over here, so by x minus 1, x plus 2, and the 5 over x plus 2 on the right, also by x minus 1, x plus 2. And so the x minus 1's divide out, that's what this is showing in the next line here. This x plus 2 and this x plus 2 divide out, that's what this is showing here. And this x plus 2 and this x plus 2, they also divide out. And so what we're left with is 4 times the x plus 2. Actually, I guess I should look at this line. 4 times the x plus 2 minus x minus 1 times the 3, that's what's here, equals 5 times this x minus 1. So I expand in, 4 times x is 4x, 4 times 2 is 8. 3 times x would be 3x, but that makes it negative. 3 times negative 1 would be negative 3, but that makes it a plus 3. 5 times x is 5x, 5 times negative 1 is negative 5. Now I want to rearrange and get all the x's on one side, isolate for x. So I'm going to bring the 5x over here, or subtract 5 from both sides. So we'd have 4x minus 3x minus 5x. And I want the numbers on the right. So I'm going to leave the negative 5 on the right. And subtracting 8 from both sides, so this is minus 8 on the right. This would become minus 3 on the right. So 4x minus 3x is 1x, minus 5x is negative 4x on the left. Negative 5 minus 8 is negative 13, minus 3 is negative 16. And then I divide out the negative 4 from the negative 4x. So negative 16 divided by negative 4 is positive 4. So that is the answer for question B. For question C here, we have these denominators x squared minus 4 here, and then this is x plus 2 and x minus 2. And the x squared minus 4, this is the difference of 2 squares, it'll factor into x minus 2 times x plus 2. So that has actually these two as its factors. So the least common denominator would actually be the product of x minus 2 and x plus 2. So that's why I'm taking this. Now notice I factored the denominator, left it like that. And I multiplied by x minus 2 times x plus 2. So this over here gets multiplied by x minus 2, x plus 2. Remember, there's a plus here, so plus here. And on the right, 2x over x plus 2 gets multiplied by the same thing. So lots of things divide out. This whole denominator will divide with this whole one. That's what that's showing. And then over here, this x minus 2 and this one will divide out. And x plus 2 and x plus 2 over here. So this whole part right here just simplifies to 6. That's 6 right there. Plus right there. and 5x minus 3 times x plus 2. And then on the right, 2x times the x minus 2. Now I need to expand this. So after the 6, x times 5x is 5x squared. X times negative 3 is negative 3x. 2 times 5x is 10x. And 2 times negative 3 is negative 6. 2x times x is 2x squared. And 2 times negative 2 is 2x times negative 2 is negative 4x. So it's a quadratic equation because I see the x squared. So I want everything on one side. It's not linear. I don't want x's on one and numbers on the other. So 5x squared here. So I'll bring this over. So minus 2x squared, or subtract 2x squared from both sides. We've got negative 3x, 10x, and then this would be a plus 4x on the left. And notice that the constant 6 minus 6 is 0, so there are no constants here. And so we get some simplification. 5x squared minus 2x squared is 3x squared. And negative 3x plus 10x would be 7x, plus 4 more makes 11x. And notice there's no constant, so I can just common factor an x out. So we get x, 3x plus 11. So if I set this x equal to 0, I get 0. Don't forget about there's a solution from that little factor there too. And then also we have to set the 3x plus 11 to 0. So when we do that, so I subtract 11 from both sides. So 3x would equal negative 11. And then we divide out the 3. Like that. And so negative 11/3 is the other solution. Question number 4 is a rational inequality. I have an inequality sign here, greater than, and we're supposed to do this algebraically and then illustrate the solution on a number line. So the first thing you do is find the restriction in this rational expression. So you set the 3x plus 6 equal to 0, because remember the denominator you don't want it to have a value of 0. That's how you find the restriction. So subtract 6 from both sides. 3x equals negative 6, and then divide it to 3, and you get negative 2. Negative 2 is what makes that have a value of 0. So there's two cases here. We have to consider below negative 2 and above negative 2. So x is less than negative 2, x is greater than negative 2. So in order to solve this, it's a rational expression, so I would multiply both sides by the 3x plus 6, and that's what's done here. 3x plus 6 times, and the same, the negative 3 gets multiplied by that 3x plus 6. Now, they divide out over here, and this simplifies to x minus 5, and then we distribute the negative 3 in here. So negative 3 times 3x would be negative 9x, and negative 3 times 6 would be minus 18. Now, because this is the case where x is less than negative 2, think of a number less than negative 2, like let's say negative 2.3 plus 6. Okay, there's my 3x plus 6. If you put a number less than negative 2 in there, notice that it's negative. And if you put a bigger number, you know, like maybe 456, okay, it's a very large negative. So any number below negative 2 is going to return a negative value. So when we're multiplying by the 3x plus 6, that's actually negative, and this inequality switches directions. See, it's greater than there, it's less than here. And if you haven't seen this before, consider this. Let's say if you look at, here's a true statement, 2 is less than 5. If I multiply that by negative 1, then the 2 becomes negative 2, and the 5 becomes negative 5. And the only way I can make that a true statement is if I reverse the inequality. Negative 2 is greater than negative 5. So that's an example of how multiplying by negative or dividing changes the direction of inequality. So that changes to a less than. Now I want to isolate for x here. So I'm going to add 9x to both sides, so plus 9x over here. And I'll add 5 to both sides, and negative 18 has 5 added to it. X and 9x is 10x, and negative 18 and 5 add to negative 13. And then we divide both sides by 10. Now, dividing by a positive 10 doesn't change the direction of inequality. So negative 13 tenths is what x is going to be less than. Now, I wrote here equals negative 1.3. You might want to see that when you go to graph in the number line. So on the number line, you graph the case and also the solution you got here. So x is less than negative 2, open circle at negative 2, and less than would mean to the left of it. This is x is less than negative 1.3. So here's about negative 1.3 right here, and we're talking about less than. Now the solution is where those two overlap. Where they overlap is actually from negative 2 to the left, below negative 2. So the solution for this part is x is less than negative 2. It's actually the case. Now in the second one, we're looking for x is greater than negative 2. So all the solving is the same. The only difference is that if we're greater than negative 2, let's put a number greater than negative 2 in here. Here's a very simple number greater than negative 2. Negative 1 is bigger than negative 2. So if I put that in place of x, notice that it works out to a positive value. And any number, oops, that was not what I meant to do. I meant to insert 7. Okay. Oh, greater than negative 2. I meant to do 27. There we go. Delete the negative. Okay, that's greater than negative 2. So notice we get a positive value. So putting any number bigger than negative 2 in place of x means that this factor has a positive value. So this does not change direction. It stays greater than. And otherwise, all the algebra is the same. Okay, we divide by 10. So x is greater than negative 1.3. Okay, so just the opposite of what we had over here, because we didn't change the direction of the inequality. So you graph the case, x is greater than negative 2. Remember, open circle because there's no equal to sign there, so just to the right of negative 2. And this would be x is greater than negative 1.3 or negative 13 tenths. Now where they overlap is actually x is greater than negative 13 tenths. So the solution there would be x is greater than negative 13 tenths. So the solution, the total solution for the whole question is x is either less than negative 2 or it's greater than negative 13 tenths. That would be the solution for number 4. For number 5, it says sketch the graph of this function. Now this is the last rational function to sketch here, and describe the special case with this graph. So this function actually will simplify. In the denominator, the x squared minus 3x minus 10 will factor, and that's what this little note is here. If we look for two numbers with a sum of negative 3 and a product of negative 10, as this is saying, you can factor that. Those numbers would be negative 5 and 2. So this denominator will factor into x minus 5 and x plus 2. The numerator, the x squared plus 2x, will also factor. We can factor an x out of it. So x plus 2 is what it factors into. And then these x plus 2's divide out. So this function actually simplifies to x over x minus 5. Now this is the special case. This x over x minus 5 function and this function are the same, except this function you can actually evaluate at negative 2. Okay, and the negative 2, I'm using negative 2 because it's the value that makes both these factors 0. So if I put negative 2 in place of this function here, I get negative 2 over negative 2 minus 5, which is negative 7. So negative 2 over negative 7 simplifies to 2 7s. They're both negative, so we divide that out to give us a positive. And so this function actually has a point that exists there, but this one doesn't. Because if I put negative 2 in place of x, these would both be 0, and it's said to be indeterminate because you have 0 divided by 0. I graphed this in Desmos. So there's the original function, x squared plus 2x over x squared minus 3x minus 10. And remember, on Desmos, if you click on the curve, and you can pull along, I'm trying to get to negative 2. You saw it there for a second. There we go. See, at negative 2, it says it's undefined. The graph doesn't exist there. If I turn this one on, there we go, and turn this one off, so I'm only graphing that one. Notice they looked exactly the same. This one, if I go over to negative 2, it actually says there's a function value there, 0.286. And that 0.286 actually comes from the 2 7s. If you go this 2 divided by 7, there's the 0.286. So that's a point on the simplified function, but not the original. So the original is said to have a hole there, and that's what this represents here, -2.27 is a hole. Otherwise, these two functions are exactly the same except for that one little place in the graph. And so we can look at this function here and find its vertical and horizontal asymptotes and intercepts and all that, and that would be the same thing for the original function. So the vertical asymptote will come from setting the x minus 5 equal to 0. And so if we solve for x, we get x equals 5, which of course is that line right there. For the horizontal, now you could take x over x or x squared over x squared. It wouldn't matter. I wrote x squared over x squared, but x divided by x would be the same. In both cases, it simplifies to 1, and so y equals 1 is the horizontal asymptote there. For the intercepts, we set 0 in place of x, and so 0 over, okay, remember this is a function, 0 over 0 minus 5 works out to 0. So if I put 0 in place of x, I get 0. So 0, 0 is actually both the x and the y-intercept. Okay, I didn't put a dot there, but you can see it goes to the origin. And then we have the end behaviors. So first of all, the horizontal, I put 100 in place of x. And remember the horizontal asymptote was y equals 1 right here. So put 100 in, and you get 1.0526. So it's getting close to 1, but it's above. So as x tends towards infinity to the far right, we're approaching 1, but from above. And so it's doing this up here. To the far left, we put negative 100 in place of x. I get a function value of positive 0.9524. So it's getting close to 1, okay, as we go to the far left, but it's approaching 1 from below. So as you pass that hole and go along to the left a long ways, you're getting higher and higher, but you approach the 1 but stay below that y equals 1 line. Remember, the vertical asymptote was x equals 5, so I did 4.99 and 5.01. So if I put 4.99, so we're to the left of the vertical asymptote a little bit, I get negative 499. So as we approach 5 from the left, y is approaching a large negative value. So as we approach from the left, the function values are getting to be large negatives. As we approach 5 from the right, I put 5.01 in place of x, and I get 501 for my function value. So as we approach 5 from the right hand side, y tends towards infinity, large positive values. So that means that as we approach the vertical asymptote from the right side, the function values are getting very large, big numbers. And that's what the graph looks like. Last page, questions 6 and 7. Number 6 here says, when polluted water flows into an unpolluted pond, the concentration of the pollutant, and C, after t number of hours, is modeled by this function. It's C of t is 20t over t plus 2000. And so C of t is measured as the percentage of the water in the pond that is polluted. What's the long-term concentration of the pollutant expected to be? And you're asked to use a few examples in the explanation. And now, just a note here, long-term would mean much more than a few days or weeks. So, now I found the concentration after 720 hours, and the reason I did 720 is because if you take 24 hours in a day times 30 days, so it's about a month. So a month is about 720 hours. A little bit more if it's 31 days, a little less if it's February. So I found the concentration after 720 days, and it works out to 5.3%. Now the 8760 was if you take 24 hours in a day times 365 days in a year. So in a year, there's 8,760 hours. So this one represents after a year. So after a year, if we put 8760 in place of time, we get 16.3%. So notice it's getting larger, and in fact, you see, if t was really big, the 2000 becomes insignificant. So for the horizontal asymptote, it's just 20t divided by t. The t's divide out, and we get 20. And you can see from this one, oh yeah, it does seem to be getting closer to 20. We could put a number bigger than 8760 in here, and it would be even closer to 20. So that means that the pollutant should approach 20% after a long period of time. Last question, number 7 here. The potential difference between electric charges is inversely proportional to the square of the distance between the charges. And now the potential difference also depends on the size of the charges, but we're going to not worry about changing them in this case. There's actually a law called Coulomb's law which details that, but we're not going to get into that. So we're told for two charges the potential difference between them is 9 Newton meters squared per Coulomb squared at a distance of 100 meters. So that's just the units for a potential difference. So we're asked in A to determine an equation that relates the potential difference between the charges to the distance between them. Now, inversely proportional. So, and I'm going to let P represent the potential difference and D is the distance. So if it's inversely proportional, P would equal a constant divided by the distance squared. That's the inversely, like 1 over the distance squared. Now we don't know what the constant is. That's what we're going to find here. If the potential difference was proportional to, then if it was, then I would just write proportional to the distance squared. Then it would just be k times d squared. But it's over d squared because it's inversely. Okay, so we can just get rid of that. So if I cross multiply, k would equal p times d squared. And this is the reason for giving this information. If the distance is 100, the potential difference is 9, so put 9 in place of p. So 100 squared is 10,000, need 4 zeros, times 9 would be 90,000. So that's the constant. So the equation would p equals 90,000 over d squared. So that's the equation we're asked to find in A. And we're going to use it in B. It says using the same charges, what is the potential difference if they are moved to only 12 meters apart? So we would put 12 in place of d here. So 90,000 divided by 12 squared is 144. So 90,000 divided by 144 is 625, and Newton meters squared per Coulomb squared would be the units for that. So at 12 meters, potential difference between them is 625 Newton meters squared per Coulomb squared. And that's the end of the solutions.